Christmas morning, 2021, a $10 billion telescope launched into darkness not to see distant worlds, but to witness time itself. What Webb found waiting in the cosmic dawn has left scientists speechless and our understanding of the universe forever changed. Where are you listening from tonight? Because tonight, we're traveling back 13 billion years to the universe's childhood, then forward through black holes, alien worlds, and the hidden web connecting everything, including you. If this quiet journey speaks to you, you're welcome to stay. Maybe leave a like or a subscribe or just listen. Let's begin. On Christmas morning, 2021, while most of the world was still wrapped in sleep and the quiet comfort of holiday warmth, something extraordinary was happening on a remote launch pad in French Guiana. The Ariane 5 rocket stood gleaming against the tropical dawn, carrying within its protective shell the most ambitious scientific instrument humanity had ever conceived. As the countdown reached 0 and the engines ignited, millions of people around the globe held their breath in collective anticipation. This wasn't just another satellite launch. This was the culmination of 30 years of dreaming, designing, and daring to imagine what might be possible if we could finally build a telescope capable of witnessing the universe's deepest secrets. The journey to this moment had been anything but simple. Since 1996, when the project was first conceived, thousands of engineers and scientists from 14 nations had poured their expertise, their sleepless nights, and their unwavering dedication into creating something that had never existed before. $10 billion, the cost of humanity's most expensive telescope, represented not just money, but countless hours of painstaking work, moments of breakthrough discovery, and periods of heart-stopping technical challenges that threatened to derail the entire mission. There were times when failure seemed inevitable, when the complexity of what they were attempting felt overwhelming. Yet they persisted, driven by a question that has haunted our species since we first looked up at the night sky. Where did we come from? Unlike its predecessor Hubble, which orbits our planet like a faithful companion, circling endlessly, just a few hundred miles above Earth's surface, Webb had a very different destination in mind. Its target was Lagrange, Point 2, or L2, as scientists call it, a special location in space, approximately 1.5 million kilometers from Earth, about 1 million miles from our home planet, roughly 4 times farther than the Moon. This isn't just an arbitrary parking spot in the cosmic void. L2 represents a gravitational sweet spot where the pull of Earth and the Sun balance perfectly, creating a stable position where Webb could float in perpetual darkness, shielded from the interfering heat and light of both our planet and our star. The 30-day journey to reach this distant outpost was itself a marvel of precision engineering, with the telescope gradually unfolding its massive sun shield and delicate mirrors in a carefully choreographed sequence so complex that a single mistake could have doomed the entire mission. The design of Webb is nothing short of extraordinary. Imagine a sun shield the size of a tennis court, composed of 5 layers of material thinner than a human hair, yet capable of providing protection, equivalent to SPF 1 million. This cosmic umbrella doesn't just block sunlight, it creates a temperature difference of hundreds of degrees between its hot and cold sides, keeping Webb's scientific instruments cooler than Pluto, at temperatures below -233 degrees Celsius. This extreme cold isn't just for show. It's absolutely essential for what Webb was designed to do. Behind this massive shield sits a golden mirror, 6.5 meters across, nearly 7 times larger than Hubble's mirror, composed of 18 precisely crafted hexagonal segments, each one coated in a microscopically thin layer of pure gold. These 18 puzzle pieces work together as one vast light-collecting surface, giving Webb the sensitivity to capture the faintest whispers of ancient starlight from the most distant reaches of space and time. But why gold? And why does Webb observe in infrared rather than visible light? The answers lie in one of the most profound truths about our universe. It's expanding and has been since the moment of the Big Bang. As space itself stretches like fabric, being pulled at the edges, the light traveling through it stretches too, like a pattern drawn on a rubber band being gradually extended. Light that left distant galaxies as visible wavelengths billions of years ago has been stretched during its long journey across expanding space, its waves growing longer and longer until they become infrared radiation wavelengths beyond what human eyes can perceive. Gold happens to be exceptionally good at reflecting these infrared wavelengths, making it the perfect coating for a telescope designed to see what we cannot. When Webb looks deep into space, it's literally looking back in time. The farther it peers into the cosmic distance, the younger the universe becomes in its view, until finally it can glimpse the cosmic dawn itself, that ancient epoch when the first stars and galaxies were just beginning to illuminate the primordial darkness. Tonight, as you lie there in the comfort of wherever you are, Webb floats in that distant darkness, a million miles from home, patiently gathering ancient photons that have traveled across unimaginable distances to reach its golden mirrors. It's like when you open an old photo album and see images from decades past, except Webb's album contains pictures taken 13 billion years ago, when the universe itself was still in its infancy, still learning how to organize matter into the magnificent cosmic structures we see scattered across the night sky today. And here's something that might make you smile. That SPF 1 million sun shield, the largest parasol ever constructed by human hands, makes even the biggest beach umbrella you've ever used look absolutely tiny by comparison. It's humanity's way of creating a pocket of cosmic cold in the midst of the sun's blazing heat, a quiet, dark sanctuary where we can finally listen to the whispers of ancient starlight without interference. But what did Webb find when it finally opened its golden eyes and peered into that ancient darkness? The answer would shake the foundations of everything we thought we knew about cosmic history. In July 2022, after months of careful calibration and nerve-wracking testing to ensure every system functioned perfectly, Webb officially began its scientific operations. Within just a few months of pointing its instruments toward the deepest reaches of space and time, it started sending back data that left the astronomical community in a state that can only be described as stunned, excited, and more than a little bewildered. These weren't just incremental improvements over previous observations. These were discoveries that challenged fundamental assumptions about how quickly the universe could organize itself after the primordial chaos of the Big Bang. Scientists around the world found themselves reaching for their textbooks, only to realize that those textbooks would need to be rewritten from scratch. The cosmic story we thought we understood was suddenly full of plot twists no one had predicted. The most shocking revelation came in May 2024 when Webb identified a galaxy designated with the rather unpoetic name JADES GS Z140, shining brilliantly in the cosmic darkness just 290 million years after the Big Bang itself. This represents what astronomers call the cosmic dawn, that brief, precious epoch when the universe's first lights were just beginning to pierce the darkness. To put this timeline in perspective that our human minds can actually grasp, imagine compressing the entire 13.8 billion year history of the universe into a single calendar year. In that cosmic calendar, the Big Bang happens at the first stroke of midnight on January 1st. Earth doesn't form until early September. Dinosaurs don't appear until Christmas Day. All of recorded human history occupies just the last few seconds before midnight on December 31st. This newly discovered galaxy, it would have been shining brightly by January 8th, when the universe was still an infant, barely out of its cosmic cradle, still learning the most basic lessons about how to create stars and structure from primordial gas. Pause for just a moment and imagine that, January 8th in cosmic time, the universe barely a week old in our year-long metaphor, and already building cities of 100 billion stars. It's like watching a newborn baby stand up and start constructing skyscrapers. Peter Van Dockum from Yale University, one of the researchers involved in this groundbreaking discovery, captured its significance perfectly when he told reporters that this galaxy represents the most distant object currently known to humanity. But more importantly, as he emphasized with barely contained astonishment, Webb was not expected to find any galaxies this early in cosmic history, at least not at this stage of the mission, and certainly not galaxies displaying the characteristics that JADES GS 140 revealed. The discovery represents far more than just setting a new record for cosmic distance. It represents a fundamental challenge to our understanding of how the universe evolved during its childhood, according to our most sophisticated models of cosmic development, models built on decades of theoretical work and refined by countless observations galaxies. This massive and this luminous simply shouldn't have had enough time to assemble themselves by this early date. The universe, at 290 million years old, should still have been relatively simple, with only the first small clumps of stars beginning to form. Yet here was Webb showing us something far more complex and organized. Think about it like discovering a fully developed ancient city, complete with sophisticated architecture infrastructure and urban planning, built in what should have been barely enough time to lay the first foundation stones. It's as if the early universe was operating with some kind of cosmic construction method. We don't yet understand a way of building complexity faster and more efficiently than our theories predict should be possible. But JADES GS Z140 wasn't a lone anomaly, a single outlier that might be explained away as a cosmic fluke. Webb continued to discover an entire population of surprisingly massive galaxies scattered throughout the early universe, each one challenging our assumptions in its own way. Some of these ancient stellar cities weighed as much as our own Milky Way galaxy, 100 billion stars worth of matter, yet they had somehow assembled themselves within just the first 700 million years of cosmic history. This wasn't one impossible galaxy. This was a whole neighborhood of them, a community of cosmic overachievers that had formed far too quickly, according to everything we thought we knew. These findings force us to confront fundamental questions about the basic mechanisms of galaxy formation. The discoveries challenge our models of how dark matter, that mysterious, invisible substance that provides the gravitational scaffolding for galaxies, behaves and clumps together in the early universe. They challenge our understanding of how efficiently stars could form from primordial gas in those ancient epochs. They even challenge the basic timeline we've constructed for how the universe evolved from the hot, dense, relatively smooth conditions shortly after the Big Bang to the complex, highly structured cosmos filled with galaxies, stars, and planets that we inhabit today. The implications extend to our understanding of how matter itself behaved under gravity's patient influence in the universe's youth. Our models suggest that dark matter should clump together gradually over hundreds of millions of years, slowly building up the gravitational wells into which normal matter can fall and form stars. But if massive galaxies were already assembled by 290 million years, or even by 700 million years, it means this process must have happened far more rapidly than we calculated. Perhaps dark matter clumped more efficiently in the early universe. Perhaps the first stars formed with unusual efficiency, converting gas into stellar mass at rates much higher than we see in modern galaxies. Or perhaps, and this is the possibility that makes cosmologists most uneasy, we need to fundamentally reconsider some of our basic assumptions about how cosmic structure formation works. The light from Jades GS Z4 0 began its journey toward us when the universe was younger than our Earth is now, traveling through expanding space for more than 13 billion years before finally encountering Webb's golden mirrors. Every photon carries within it information about conditions in that ancient epoch, a message in a bottle thrown across cosmic time. And the message is startlingly clear. The early universe was not the quiet, slowly developing place we imagined. It was vigorous, dynamic, and capable of creating complexity at speeds that our current theoretical frameworks struggle to explain adequately. It's a bit like discovering a 2-year-old child who can already solve differential equations. Not impossible, perhaps, but certainly requiring us to reconsider everything we thought we understood about developmental timelines and the processes that lead to sophisticated capabilities. The universe, it seems, was a remarkably precocious child, indeed, reaching developmental milestones far earlier than any of our cosmic pediatricians had predicted. But discovering when these ancient galaxies formed was only the beginning. Webb's instruments could do something even more remarkable. They could analyze the very chemistry of these distant stellar cities, revealing secrets about the cosmic recipes that built the universe. Webb isn't just a camera pointing at distant objects, capturing pretty pictures of cosmic vistas. It's a flying laboratory equipped with spectroscopic instruments so sensitive they can break down the light from galaxies billions of light years away into its component wavelengths, revealing the chemical fingerprints hidden within that ancient starlight. Think of it like a cosmic DNA analyzer, but instead of reading genetic code, it's reading the elemental composition of stars that died before our solar system even existed. Every chemical element in the universe has its own unique signature, a specific pattern of wavelengths it absorbs or emits when heated. Hydrogen has its pattern, helium, another carbon, yet another. These spectral fingerprints are as distinctive as human fingerprints, and they never lie. By examining the light from distant galaxies through Webb's spectrographs, astronomers can determine exactly what these ancient stellar systems are made of, even though they're so far away that their light has been traveling toward us for most of cosmic history. When Webb turned its spectroscopic instruments toward those surprisingly massive early galaxies we discussed earlier, astronomers expected to find chemical compositions broadly similar to what we observe in our own cosmic neighborhood, perhaps with lower abundances of heavy elements, since fewer generations of stars had lived and died to enrich the cosmic gas. What they found instead was completely unexpected and profoundly puzzling. The early galaxies displayed unusually high amounts of nitrogen, far more than we observe in our sun and the stars in our local stellar community. Meanwhile, most other heavy elements were present in much lower quantities than our models predict should exist at that stage of cosmic evolution. The ratios were all wrong. The cosmic recipe book seemed to be written in a language we couldn't quite read. This discovery is far more significant than it might initially appear. You see, in the beginning, in those first moments after the Big Bang, the universe contained only the simplest elements, hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon that makes up our bodies, every molecule of oxygen. We breathe every bit of iron in our blood, and calcium in our bones had to be created later through stellar alchemy. Stars are the universe's element factories. In their incredibly hot, dense cores, they fuse lighter elements into heavier ones through nuclear fusion, the same process that makes them shine. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. In the most massive stars, this process continues up the periodic table, creating nitrogen, oxygen, silicon, iron, and dozens of other elements. When these massive stars reach the end of their lives and explode as supernovas, they scatter these newly forged elements across vast regions of space, enriching the cosmic gas from which the next generation of stars will form. This cycle of stellar birth element creation and explosive death should follow predictable patterns. We've built sophisticated models of stellar evolution that tell us how quickly different elements should accumulate in galaxies over time. These models have been tested against observations of stars in our own galaxy and nearby galaxies, and they generally work quite well. But the early galaxies Webb is observing don't follow the script. The elevated nitrogen levels, combined with the surprisingly low abundances of other heavy elements, suggest that stellar evolution in the early universe was operating according to rules we haven't fully grasped. It's as if we discovered ancient metallurgists who somehow produced high-carbon steel alloys using techniques that modern materials engineers can't explain, or reproduce a cosmic craftsmanship that challenges our understanding of the fundamental processes involved. Several theories are emerging to explain these strange chemical signatures. Perhaps the first generation of stars, those formed from the pristine primordial gas, containing only hydrogen and helium were fundamentally different from stars forming today. Maybe they were more massive on average, or maybe they exploded differently, preferentially releasing certain elements into space while retaining others. Perhaps there were unusual nuclear reaction pathways in the extreme conditions of the early universe that we haven't accounted for in our models. Or perhaps the mixing of elements in early galaxies happened differently than it does today, creating pockets of gas with very different compositions from the average. Each of these possibilities has profound implications for our understanding of how stars drive the chemical evolution of galaxies, the gradual process by which the cosmos transforms from a universe of simple elements into one rich with the complex chemistry necessary for planets and life. These aren't just abstract questions about ancient cosmic history. These strange elemental ratios connect directly to our own existence. Because the chemical evolution of galaxies ultimately determined what kinds of planets could form and where. The carbon in the organic molecules that make up every cell in your body, the oxygen you're breathing right now, the iron that helps your blood carry that oxygen to your tissues, the calcium that gives structure to your bones. All of these elements were created in the cores of massive stars and scattered through supernova explosions billions of years ago. Understanding how this chemical enrichment proceeded in the early universe helps us understand the conditions that eventually made planets like Earth possible. It helps us understand the origin story not just of galaxies and stars, but of the very elements that make our existence possible. When Webb peers at these distant galaxies and detects their unusual nitrogen abundances, it's not just making an interesting astronomical observation. It's revealing gaps in our understanding of the cosmic processes that led from the simple post-Big Bang universe to the chemically complex cosmos we inhabit today. We're still missing pieces of the puzzle. We don't fully understand the cosmic recipe book, the full set of processes by which stars create and distribute heavy elements throughout galaxies. And until we understand that recipe book completely, we can't fully understand our own origins, because we are literally made from stardust, from atoms forged in stellar cores and scattered through cosmic violence long before our sun was born. Those strange elemental abundances in distant galaxies represent a mystery that connects the most ancient epochs of cosmic history to the most intimate aspects of our own existence. Through billions of years of stellar alchemy and galactic evolution, those peculiar ratios of nitrogen and other elements eventually contributed to the enrichment of the gas cloud that would one day collapse to form our solar system. Some of those nitrogen atoms might now be in the proteins in your cells. Some of those carbon atoms might be in the DNA that makes you uniquely you. Understanding the cosmic chemistry of the early universe isn't just about understanding distant galaxies. It's about understanding ourselves and tracing our atomic lineage back to the universe's childhood, to that strange epoch when stellar chemistry followed rules we're only beginning to decipher. The mysteries deepen when we look not just at the chemistry of these ancient galaxies, but at their physical shapes and structures. What Webb revealed about the architecture of early galaxies was, if anything, even more surprising. When you look at images of modern galaxies in our cosmic neighborhood, relatively close to us, in space and time, you see familiar patterns. There are elegant spiral galaxies like our own Milky Way, with their graceful curved arms of stars wrapping around a bright central bulge. There are elliptical galaxies, smooth and featureless, shaped like cosmic footballs or spheres. We understand these shapes reasonably well. Spiral galaxies are active, still forming stars, their arms traced by bright young stellar populations. Elliptical galaxies are older and quieter, having long ago exhausted or lost their star-forming gas. This classification scheme has worked well for decades, helping astronomers understand the galaxy population in our cosmic neighborhood. But when Webb turned its infrared gaze toward the most distant galaxies, galaxies seen as they appeared in the universe's first billion years, it revealed something completely unexpected. These ancient galaxies don't look like their modern descendants. Webb's observations have shown that many distant galaxies display flattened oval disc-like and even tube-like structures that don't fit neatly into our familiar categories of spirals and ellipticals. Some look stretched and elongated, like cosmic cigars floating in the void. Others appear as flat disks, but without the organized spiral structure we see in nearby galaxies. Still others show irregular lumpy morphologies that suggest they're still in the process of assembling themselves, not yet settled into the stable configurations we observe in the modern universe. These shapes were completely unexpected. Our theoretical models of galaxy formation didn't predict this diversity of morphologies in the early universe. It's as if we opened an ancient architecture textbook and found that the buildings followed completely different design principles than anything in modern construction structures that are both functional and, in their own way, beautiful, but operate according to engineering rules we're only beginning to understand. The contrast with modern galaxies is striking and significant. Today's universe is dominated by two main galactic architectures: the graceful spirals with their organized rotational patterns, and the smooth ellipticals with their random stellar orbits. But in the universe's youth, galaxies appear to have explored a much wider range of possible shapes and configurations. This suggests that galaxy formation in the early universe followed pathways that our current theories struggle to fully explain. Perhaps the gas from which these galaxies formed had different properties than the gas in modern star-forming regions. Perhaps the dark matter halos, the invisible gravitational structures within which galaxies form, had different shapes or density profiles in the early universe. Perhaps the frequent collisions and mergers between young galaxies created these unusual morphologies as temporary way stations on the journey toward more familiar shapes. What makes these observations particularly intriguing is that they force us to reconsider our understanding of how galaxies settle into stable configurations. We thought we understood this process reasonably well. Gas collapses into a dark matter halo, begins to form stars, and gradually settles into a rotating disk, or through mergers and interactions into an elliptical galaxy. But the early galaxies Webb is observing seem to have been doing something different, following formation pathways that produced these strange, unfamiliar architectures. It's like discovering that ancient civilizations built their cities according to urban planning principles, completely different from anything modern architects would recognize. Yet somehow, their cities functioned, housed populations, and in some cases thrived for centuries. But perhaps the most haunting discoveries Webb has made about early galaxies involve those that astronomers call dead galaxies, stellar systems that have completely ceased forming new stars. These galactic graveyards represent the remnants of intense star formation episodes during the cosmic dawn galaxies that burned through their available gas, incredibly quickly, creating vast populations of stars in brief, furious bursts before exhausting their fuel and falling into a kind of stellar hibernation. Previous telescopes, including Hubble and ground-based instruments, had detected hints of these dead galaxies in the early universe, but they couldn't gather enough light or achieve sufficient spectroscopic detail to determine exactly when these galaxies had stopped forming stars or how long they'd been dormant. Webb changed that. With its unprecedented sensitivity and spectroscopic capabilities, Webb can dissect the light from these distant dead galaxies with extraordinary precision, revealing the ages of their stellar populations and determining how long ago star formation ceased. It's like having a cosmic forensics laboratory that can examine not just that something died, but when it died, how it died, and what it looked like in its prime. These dead galaxies provide crucial clues about the life and death cycles of galaxies in the early universe. Why did some galaxies exhaust their star-forming gas so quickly, while others, like our own Milky Way, continued forming stars over billions of years? What processes can shut down star formation so completely that a galaxy becomes essentially sterile, unable to create new stellar generations? Several mechanisms might explain these early galactic deaths. Perhaps some galaxies formed in regions where the gas was quickly heated to such high temperatures that it could no longer collapse to form stars. Perhaps the first supermassive black holes in these galaxies' cores grew so rapidly that their energy output blew away or heated up all the remaining star-forming gas. Perhaps early galaxy mergers were sometimes so violent that instead of triggering star formation, they actually disrupted the gas and expelled it from the galaxies entirely. Each of these scenarios is possible, and Webb's observations are beginning to provide the evidence needed to determine which processes were most important in the early universe. Understanding these galactic life cycles, why some galaxies live long, active lives, while others burn out young, is crucial for understanding the full story of cosmic evolution. It helps us understand why our own galaxy has the properties it does, why it continues to form stars at a relatively steady rate, rather than having exhausted its gas billions of years ago. It helps us understand the diversity of galactic environments across the cosmos, and which types of galaxies are most likely to host planetary systems and potentially life. These ancient dead galaxies aren't just curiosities from cosmic history. They're key pieces of evidence in our effort to understand the forces that shape galaxies and determine their fates. We're gradually fitting these puzzle pieces together: the unusual chemistries, the strange morphologies, the surprisingly early galactic deaths, building toward a more complete picture of how the universe organized itself during its childhood. The architecture of those early galaxies, so different from what we see today, tells us that cosmic evolution has been a journey with many pathways, many experiments, many evolutionary dead ends, and successful innovations. The universe was learning how to build galaxies, trying different approaches, and the results of those ancient experiments are written in the light that Webb is now capturing and decoding for us. These discoveries, the impossible galaxies, the strange chemistries, the unfamiliar architectures, all point to something profound. We're witnessing the moment when our theoretical understanding of the universe collides with actual observations from its earliest epochs. And that collision is changing everything. For decades before Webb launched, cosmologists lived in a world built primarily on theoretical foundations and computer simulations. They had elegant mathematical models describing how the universe should have evolved from the Big Bang to the structured cosmos we observe today. They ran sophisticated simulations, modeling dark matter behavior, gas collapse, the first stars, and the gradual assembly of galaxies. These models were impressive achievements, incorporating our understanding of gravity, thermodynamics, nuclear physics, and countless other principles. But they had one fundamental limitation. They were largely untested against actual observations from the earliest epochs of cosmic history. Before Webb astronomers had to extrapolate backward from relatively nearby galaxies, objects only a few billion light-years away, seen when the universe was already several billion years old and considerably matured. It was like trying to understand ancient history without any archaeological artifacts, without written records, with nothing but modern societies to study and theories about how they might have evolved. You could make educated guesses and build plausible models, but you couldn't really know if your theories matched reality because you had no direct evidence from the periods you were trying to understand. The cosmic dawn remained largely theoretical territory, a realm of educated speculation rather than observational fact. Webb changed everything. For the first time, we have actual observational data from the cosmic dawn itself, not extrapolations, not educated guesses, but actual photons from those ancient galaxies that traveled 13 billion years to reach Webb's golden mirrors. The telescope provides a direct window into the universe's childhood, filling the enormous gap between the theoretical Big Bang and the mature galaxies we observe nearby. As one researcher beautifully expressed it, up until James Webb, we never actually had observational data to help us understand the physics of the early universe. We're moving from a realm where theory dominated because observations were impossible into one where observations can now test, challenge, and refine our theories. The observations have sparked intense debates. Some scientists propose that star formation in the early universe must have been extraordinarily efficient, far more so than in the modern cosmos. If primordial gas could convert to stars at much higher rates, it would help explain how massive galaxies assembled so quickly. Perhaps early gas had properties making it easier to collapse. Perhaps the first stars were more massive, living shorter lives, but creating heavy elements more rapidly. These scenarios could explain the early massive galaxies without fundamentally revising our cosmology. But others suggest something more radical. We may need to reconsider dark matter itself. Dark matter, that mysterious substance outweighing ordinary matter, 5-1, provides the invisible scaffolding around which galaxies form. If early galaxies formed faster than predicted, perhaps dark matter behaved differently in the universe's youth, clumping more efficiently and allowing ordinary matter to collapse more rapidly. Revising our understanding of dark matter would represent a profound shift, as it's one of cosmology's fundamental components. We're potentially witnessing the most significant paradigm shift since 1929, when Edwin Hubble discovered the universe is expanding. That single observation transformed cosmology from a static field into a dynamic science, studying cosmic evolution. Webb's discoveries may be comparably revolutionary. The telescope shows us that cosmic evolution proceeded faster, more efficiently, and more dramatically than we imagined. The universe wasn't gradually building complexity, it was racing ahead, creating massive galaxies with startling speed, and Webb has only just begun. These discoveries represent initial findings from the first couple years of operation. Webb is designed to function for at least a decade. Each observation adds new chapters to our understanding. What we've explored tonight represents just the opening pages of an epic tale that will continue unfolding as this remarkable machine peers deeper into space and further back in time than any instrument before it. Each discovery from Webb doesn't just change astronomy textbooks, it changes how you see the night sky when you step outside. Every star is part of a galaxy that formed through these processes we're now observing. The elements in your body were created through stellar evolution under these mysterious conditions Webb reveals. As you close your eyes tonight, know that Webb continues its patient work in the darkness 1,000,000 miles from home, gathering ancient photons that have traveled across most of cosmic history. With each passing second, it looks deeper into the past, revealing how the universe transformed from simplicity to the magnificent cosmos we're part of. The journey continues. We've explored the time machine's view of the cosmic dawn, but Webb's reach extends beyond the distant past. In our next chapter, we'll encounter different cosmic mysteries, monsters lurking in darkness, objects so massive they bend space and time itself, giants that shouldn't exist feeding at impossible rates, shaping the destiny of galaxies. Rest well knowing the universe is stranger and more wonderful than we ever imagined. From the impossible galaxies of the cosmic dawn, we now turn our attention to the most extreme objects in the universe. Cosmic monsters so massive that they warp the very fabric of reality around them. To understand what Webb has discovered lurking in the hearts of ancient galaxies, we first need to understand what black holes actually are. Imagine a region of space where gravity has become so overwhelmingly powerful that it warps the fabric of space and time itself into an inescapable trap. At the center of this trap sits a point of infinite density, a singularity where all the rules of physics as we know them break down completely. Around this singularity lies the event horizon, an invisible boundary that marks the point of no return. Anything that crosses this boundary matter, light information can never escape. The gravitational pull is so intense that not even light traveling at 300,000 kilometers per second can break free. Black holes are literally holes in the visible universe regions from which no information can return to tell us what's happening inside. These cosmic monsters aren't just theoretical curiosities. They're real objects scattered throughout the universe, and they play crucial roles in cosmic evolution. We now know that supermassive black holes, objects millions or even billions of times more massive than our Sun, lurk at the centers of most large galaxies, including our own Milky Way. Our galaxy's central black hole, called Sagittarius A Mars, pronounced Sagittarius A star, weighs about 4 million times as much as the Sun. That might sound enormous, but compared to what Webb has discovered in the early universe, Sagittarius A is actually quite modest. These supermassive black holes aren't passive objects sitting quietly in galactic cores. They fundamentally shape how galaxies evolve, regulating star formation, influencing the flow of gas throughout their host galaxies, and in many cases, powering the most energetic phenomena in the entire cosmos. In May 2024, Webb made a discovery that left astrophysicists genuinely stunned. In the constellation Telescopium, the telescope detected a small red compact object that existed just 500 million years after the Big Bang, an epoch when the universe was barely 3% of its current age. This unassuming little red dot harbors what may be the earliest known black hole in the universe, and its properties are nothing short of mind-bending. The black hole at the center of the galaxy, Sears LRDZ9, weighs approximately 38 million times the mass of our Sun, making it roughly 10 times more massive than Sagittarius A, the supermassive black hole anchoring our own Milky Way. But here's what makes this discovery truly impossible to reconcile with our theories. This ancient black hole contains about 5% of the total mass of all the stars in its host galaxy. To understand why this ratio is so shocking, consider that in the modern universe, supermassive black holes typically contain only about 0.1% of their host galaxy's stellar mass. The black hole in Sears LRDZ9 has 50 times more mass relative to its galaxy than what we observe in nearby mature galaxies. It's a completely disproportionate relationship that challenges everything we thought we understood about how black holes and galaxies grow together over cosmic time. Stephen Finkelstein, one of the astronomers involved in this groundbreaking discovery, captured the significance perfectly when he noted that this adds to growing evidence that early black holes grew much faster than we thought possible, or they started out far more massive than our models predict. Either possibility requires us to fundamentally reconsider our understanding of black hole formation and growth. The problem is rooted in basic physics. Black holes grow by consuming matter, gas dust stars. Anything that ventures too close to the event horizon gets pulled in and adds to the black hole's mass. But there's a theoretical limit to how fast this feeding can occur, determined by the balance between gravity pulling matter inward and radiation pressure pushing it outward. As matter falls toward a black hole, it heats up tremendously, emitting intense radiation. This radiation creates an outward pressure that can actually prevent more matter from falling in. The balance between these competing forces sets what's called the Eddington limit, a theoretical maximum rate at which a black hole can grow by consuming surrounding matter. According to this limit, even under ideal conditions with unlimited available matter, it should take hundreds of millions of years for a black hole to grow from stellar origins to millions of solar masses. Yet here's Webb showing us a black hole that somehow reached 38 million solar masses within just 500 million years after the Big Bang. The timeline simply doesn't work. According to conventional physics, it's like discovering a 6-month-old baby who already weighs 50 kilograms, not just surprising, but forcing us to reconsider everything we thought we understood about growth and development. Either these early black holes were fed at rates that somehow exceeded the theoretical Eddington limit, or they started their existence already much more massive than a typical stellar mass black hole, or there are physical processes operating in the early universe that our current theories simply don't account for. The implications ripple far beyond just understanding black holes themselves. These discoveries challenge our understanding of galaxy formation because black holes and galaxies appear to evolve together in an intricate cosmic dance. The relationship between supermassive black holes and their host galaxies isn't coincidental, it's fundamental. In the modern universe, we observe tight correlations between black hole mass and various properties of the surrounding galaxy. More massive galaxies harbor more massive black holes, and this relationship suggests they influence each other's growth. Black holes can regulate star formation by heating or expelling gas that would otherwise form new stars. Conversely, galaxies feed their central black holes by funneling gas toward the galactic core through various processes. Webb's observations suggest this intimate relationship was established very early in cosmic history, meaning that supermassive black holes weren't just passengers along for the ride. They were active participants in shaping the universe's structure and evolution from the very beginning. Fortunately for us, the supermassive black hole, the center of our own Milky Way, is far more modest and well-behaved than these early cosmic monsters. And at 26,000 light-years away from our solar system, Sagittarius A is distant enough that we can rest peacefully, safely outside its gravitational influence as these cosmic investigations continue to unfold and challenge our understanding of the universe's most extreme objects. But these solitary, massive black holes weren't the only shock Webb had in store. The telescope also witnessed something even more violent the moment when two of these cosmic monsters collide and merge into one. In May 2024, Webb identified evidence of the most distant black hole merger ever observed by human instruments. Within the galaxy system, Zaya 7, the telescope detected two massive black holes in the process of spiraling toward each other and combining, an event occurring just 740 million years after the Big Bang. This represents not merely a new record for observational distance, but the first time such a phenomenon has been detected so early in cosmic history. The discovery opens a window into understanding how supermassive black holes achieved their enormous masses in the universe's youth through violent collisions that released more energy than anything else in the cosmos. Black hole mergers rank among the most energetic events in the entire universe. When two supermassive black holes spiral into each other and finally merge, they release staggering amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. that propagate outward at the speed of light. To put the energy scale in perspective, during the final moments of a black hole merger, the system radiates more power in gravitational waves than all the stars in the observable universe combined emit in electromagnetic radiation. It's not that the merger is brighter than all those stars' gravitational waves, and light are fundamentally different forms of energy, but the sheer power output is greater than everything else happening in the visible cosmos at that moment. The collision literally shakes the structure of space-time, creating ripples that travel across billions of light years, carrying information about the catastrophic event that created them. These gravitational waves were predicted by Einstein's general theory of relativity over a century ago, but they weren't directly detected until 2015, when the LIGO Observatory in the United States picked up the distinctive signal of two stellar mass black holes merging about 1.3 billion light years away. Since then, LIGO and its European counterpart Virgo have detected dozens of such events, gradually building our understanding of how common black hole mergers are and what happens during these cosmic collisions. But all of those detections involved relatively nearby events and relatively small black holes, typically tens of times the Sun's mass. Webb's observation of a merger in ZS7 shows us that these violent processes were already occurring when the universe was barely 5% of its current age, and involving black holes millions of times more massive. The significance of this discovery extends beyond just setting another distance record. It reveals that black hole mergers were frequent events in the early universe, and this frequency helps explain the puzzle we discussed earlier, how supermassive black holes grew so large so quickly. If you start with a modestly sized black hole, and it can only grow by slowly consuming gas at rates limited by the Eddington limit, you run into timeline problems. But if black holes can also grow through mergers by colliding with and absorbing other black holes, then the growth can proceed much faster. Each merger instantly doubles the mass, or at least adds a substantial fraction. A series of mergers over a few 100 million years could plausibly build up a black hole to tens of millions of solar masses, helping to explain those impossibly massive early black holes that Webb keeps discovering. The combination of rapid growth through gas accretion and frequent mergers creates a pathway to forming supermassive black holes within the brief timeline available in the early universe. It's as if the cosmos discovered two different mechanisms for building these massive objects and employed both simultaneously, accelerating the growth process through this dual approach. But Webb has revealed even more exotic scenarios for black hole formation. In the Cosmos Webb survey, astronomers discovered an unusual object nicknamed the Infinity Galaxy. Because of its distinctive shape, it displays two compact red nuclei surrounded by rings of material, creating a pattern that resembles the mathematical infinity symbol. This bizarre structure appears to have formed through the head-on collision of two disk galaxies, a cosmic train wreck playing out over millions of years. What makes it truly remarkable is the supermassive black hole positioned between the two nuclei, sitting within a vast expanse of gas. The research team proposes that this central black hole may have formed through what's called direct collapse of the gas cloud itself. This represents a fundamentally different pathway to creating massive black holes. Instead of starting small and growing gradually, the black hole forms already massive through the catastrophic collapse of an enormous cloud of primordial gas. Under the right conditions, specifically in a gas cloud that's extremely hot and metal poor, normal star formation can be suppressed. Instead of fragmenting into many smaller clouds that each form individual stars, the entire massive cloud can collapse directly into a black hole weighing millions of times the mass of the Sun. It's a cosmic shortcut, allowing black holes to skip the usual slow growth process and begin their existence already enormous. This direct collapse scenario is like discovering that some mountains didn't form gradually through tectonic uplift and erosion over millions of years, but instead appeared fully formed when enormous chunks of rock were dropped from space. It's a different pathway to the same end result, but one that operates on dramatically faster timescales. The infinity galaxy may be showing us this process in action, providing observational evidence for a theoretical mechanism that could help explain how the universe managed to create supermassive black holes so quickly after the Big Bang. These merger observations and direct collapse candidates aren't just interesting astrophysical phenomena. They're pieces of the puzzle, explaining how the universe organized itself during its childhood. The ancient mergers Webb is witnessing helped shape the structure of our own galaxy. The processes that created those early supermassive black holes, through rapid growth and violent collisions, eventually led to the formation of Sagittarius A and the Milky Way as we know it. It's like watching ancient cities merge and combine, understanding that those historical consolidations ultimately led to the modern urban landscape we inhabit today. Every discovery about early black holes teaches us something about our own cosmic origins and the violent processes that created the structured universe we call home. These mergers help explain how black holes grew so massive so quickly, but Webb discovered something even more extreme: black holes that weren't just growing fast, but feeding at rates that physics says should be impossible. We've established that black holes grow by consuming matter, by pulling in gas dust and anything else that ventures too close to their gravitational embrace. But this feeding process isn't unlimited. There's a fundamental speed limit built into the physics, a maximum rate at which a black hole can consume matter. And this limit is called the Eddington limit, named after the British astrophysicist Arthur Eddington, who first calculated it in the 1920s. Understanding this limit is crucial to grasping just how shocking Webb's latest discoveries truly are. Here's how the Eddington limit works. When matter falls toward a black hole, it doesn't simply plunge straight in like water down a drain. Instead, it typically forms a swirling disk around the black hole, an accretion disk, where the material gradually spirals inward. As this matter gets closer to the event horizon, it's compressed and heated to extraordinary temperatures, sometimes millions of degrees. This superheated material doesn't just get hot, it begins to radiate intensely, emitting enormous amounts of energy in the form of light X-rays and other electromagnetic radiation. This radiation paradoxically creates a problem for the black hole's continued feeding. The outward pressure from all that radiation pushes against infalling material, acting like a cosmic wind. that tries to blow away the very gas the black hole is trying to consume. The Eddington limit represents the point where these two forces, gravity pulling material inward and radiation pressure pushing it outward, reach a balance. Above this rate, the radiation pressure becomes so intense that it should effectively blow away the accretion disk, shutting down the feeding process and preventing the black hole from growing any faster. It's a self-regulating mechanism that nature has built into the physics of accretion. For any given black hole mass, you can calculate the maximum luminosity it can produce, and therefore the maximum rate at which it can accrete matter. This limit has been tested and confirmed through countless observations of black holes in our cosmic neighborhood, and it's been built into every model of black hole growth for decades. It's considered one of the fundamental constraints on how quickly black holes can develop. Then Webb, working in conjunction with NASA's Chandra X-ray Observatory, identified something that simply shouldn't exist according to this well-established physics. The combined observations revealed a low-mass supermassive black hole existing 5 billion years after the Big Bang, already an interesting find on its own. But what made it truly extraordinary was how this black hole was behaving. The data showed unmistakably that this black hole was consuming matter at a rate more than 40 times faster than the Eddington limit should allow, not just slightly exceeding the theoretical maximum, but absolutely shattering it by a factor of 40. This phenomenon, which astronomers somewhat understatedly call super Eddington accretion, represents one of the most extreme violations of conventional astrophysical expectations that Webb has discovered. To put this in perspective with a more familiar analogy, imagine a bathtub with a drain. Water flows in through the faucet and out through the drain. Now imagine discovering that somehow the drain is removing water faster than you're adding it through the faucet. Not just a little faster, but 40 times faster. The bathtub would be emptying itself faster than physically possible given the inflow rate. This is essentially what this black hole is doing. According to our understanding of physics, the radiation pressure it's generating should be blowing away the incoming material. The rate of inflow should be self-limiting, yet somehow matter is falling into this black hole at rates that should be impossible to maintain. Physics says this cannot happen, but the black hole apparently didn't read the textbook. If physics could speak, it might be saying, "That's impossible," while the black hole replies, "Hold my beer and watch this." Several theoretical mechanisms might explain how super Eddington accretion could occur, though none are fully proven. Perhaps the infalling material is somehow shielded from the radiation pressure. Maybe it's clumpy or comes in preferentially from certain directions where the radiation is weaker. Perhaps the geometry of the accretion disk is different from what we assume, allowing material to fall in through channels where radiation pressure is less effective. Perhaps there are magnetic fields helping to funnel material inward against the outward radiation pressure. Or perhaps the radiation itself is somehow beamed in specific directions rather than radiating isotropically, which would mean the black hole could accrete faster without generating the expected outward pressure. Each of these scenarios is theoretically possible, but would require conditions significantly different. from the standard models we use to understand black hole feeding. Haewon Soo from the International Gemini Observatory, who led the research team that analyzed this extraordinary system, explained the significance beautifully. She noted that this discovery suggests a significant portion of mass growth can occur during a single episode of rapid feeding, regardless of whether the black hole originated from a light or heavy seed. This statement might sound technical, but it carries profound implications. What she's saying is that a black hole doesn't need to start out massive to become massive quickly. Even a relatively small black hole, if it can undergo one or more of these super Eddington feeding frenzies, can rapidly bulk up to enormous size in a cosmically brief period. These feeding episodes, while they probably don't last very long in astronomical terms, perhaps a few million years at most, are so efficient at adding mass that they could account for substantial fractions of a black hole's total growth. This discovery helps solve the puzzle we've been building throughout this chapter. Remember those impossibly massive early black holes that Webb keeps finding? Black holes that reached tens of millions of solar masses within just a few 100 million years after the Big Bang. We've now identified 3 potential pathways that could explain their rapid growth. First, direct collapse can create black holes that start out already massive, skipping the slow early growth phase entirely. Second, frequent mergers can add mass in sudden, large increments rather than gradual accumulation. And third, super Eddington accretion episodes can allow black holes to feed far faster than the theoretical limits we thought constrained their growth. Individually, each of these mechanisms helps, but combined together, they create a powerful explanation for how the universe managed to build supermassive black holes so quickly. The early universe, it turns out, was something of a paradise for black hole growth, a cosmic feeding ground where conditions were optimal for rapid development. The gas was denser and more abundant than in the modern universe. Galaxies were closer together, making mergers more frequent. The first generation of massive stars produced abundant stellar mass black holes that could serve as seeds, and apparently, under the conditions that prevailed in the universe's youth, super Eddington feeding was not just possible, but perhaps even common. All of these factors working together created an environment where black holes could grow with remarkable efficiency, racing from stellar masses to millions or even billions of solar masses in timescales that seem impossibly brief by modern standards, but were apparently routine in the cosmic dawn. These discoveries about black hole feeding aren't just interesting astrophysical curiosities. They're revealing fundamental truths about how the universe organized itself during its earliest epochs. The relationship between supermassive black holes and their host galaxies, a relationship we observe being so important in shaping galactic evolution, was apparently established very early through these rapid growth processes. Black holes weren't late additions to galaxies that had already formed. They were growing alongside their host galaxies from the very beginning, influencing star formation, regulating gas flows, and helping to determine what kinds of stellar populations would ultimately develop. The monsters at the hearts of galaxies have been shaping cosmic evolution since the cosmic dawn, and Webb is finally showing us how they achieved their monstrous sizes so quickly. The universe, as we're discovering through Webb's observations, is far more dynamic, far more extreme, and far more capable of pushing against the theoretical limits we've calculated than we ever imagined. From the impossible early galaxies to the impossibly massive early black holes to the impossibly fast feeding rates, each discovery is forcing us to reconsider what we thought were firm boundaries on cosmic behavior. The universe, in its youth, was not a gentle, slowly evolving place, but a realm of extremes where rapid change and violent processes were the norm rather than the exception. From these cosmic monsters feeding at impossible rates, we now turn to the opposite extreme objects that failed to become stars at all, yet hold their own fascinating secrets. After exploring the most massive objects in the universe, it's time to turn our attention to cosmic failures, or at least that's what astronomers have traditionally called them. Brown dwarfs occupy a peculiar twilight zone in the cosmic bestiary. They're objects caught between being planets and being stars too massive to be considered planets, but lacking the mass necessary to become true stars. Understanding what makes them different requires understanding what makes a star in the first place. Stars shine because of nuclear fusion occurring in their cores. In the immense pressures and temperatures at a star's center, hydrogen atoms are forced together with such violence that they overcome their natural electrical repulsion and fuse into helium, releasing tremendous amounts of energy in the process. This is the fire that powers every star in the universe, from small red dwarfs, barely massive enough to maintain fusion, to supergiant stars hundreds of times more massive than our sun. But fusion doesn't ignite automatically. It requires specific conditions. Particularly, it requires enough mass that the gravitational compression at the core generates sufficient temperature and pressure. The minimum mass needed to sustain hydrogen fusion is roughly 75 to 80 times the mass of Jupiter, which translates to about 7.5% of the Sun's mass. Brown dwarfs fall below this critical threshold. They're more massive than any planet, typically at least 13 times Jupiter's mass, which is the point at which objects can fuse deuterium-heavy hydrogen, but not regular hydrogen, but less massive than the minimum needed for sustained hydrogen fusion. Without that nuclear fire in their cores, brown dwarfs don't truly shine. They do emit radiation, primarily in infrared wavelengths, but this glow comes from leftover heat from their formation gradually radiating away into space, not from ongoing nuclear reactions. They're cosmic failures in the sense that they tried to become stars, but didn't quite make it. They gathered mass through gravitational collapse, just like stars do, but stopped growing before crossing the threshold into stellar existence. Hence the nickname, failed stars. Though this moniker perhaps doesn't fully capture how interesting these objects actually are. Before Webb launched, astronomers had cataloged approximately 3,000 brown dwarfs, all of them residing within our own Milky Way galaxy. These objects are relatively nearby in cosmic terms, close enough that we can study them in some detail. But there was a significant limitation. We could only observe brown dwarfs in our local galactic environment, where conditions are relatively enriched with heavy elements after billions of years of stellar processing. We had no observations of brown dwarfs in truly different environments, in regions where the gas is more pristine, more similar to conditions in the early universe, or in regions with different metallicities or different stellar populations. We simply didn't have telescopes powerful enough to detect these dim objects at extragalactic distances. Webb changed that limitation dramatically. Elena Sabi from the Space Telescope Science Institute led a team that used Webb to identify the first rich population of brown dwarf candidates beyond our galaxy. They found these objects in the star cluster NGC 602, a young cluster situated in the Small Magellanic Cloud, a dwarf galaxy that orbits our Milky Way at a distance of about 200,000 light years. This might not sound particularly far in cosmic terms. NGC 602 is practically next door compared to the billions of light years we've been discussing for early galaxies. But for brown dwarfs, which are intrinsically very dim objects, detecting them at this distance represents an extraordinary achievement. More importantly, the environment in NGC 602 is significantly different from our solar neighborhood. The gas in this region is metal poor, meaning it contains lower abundances of elements heavier than hydrogen and helium, more similar to conditions that prevailed in the early universe. The significance of this discovery extends far beyond simply adding to our census of known brown dwarfs. By studying these young, metal-poor brown dwarfs in an environment completely different from our local galactic neighborhood, astronomers are gaining insights into how stars and substellar objects formed under the harsh conditions that prevailed in the early universe. It's like discovering artifacts from an ancient civilization in a previously unexplored region, artifacts that reveal how people lived and worked under conditions completely unlike anything in the modern world. These brown dwarfs in NGC 602 formed from gas that more closely resembles the primordial material from which the first generation of stars condensed. By understanding how brown dwarfs form in such environments, we learn something fundamental about the star formation process and how it might have operated in the cosmic dawn. But Webb didn't stop at finding brown dwarfs in other galaxies. The telescope also pushed the boundaries of what we thought possible in star formation itself by identifying the new record holder for the smallest free-floating brown dwarf ever discovered. Kevin Luhman from Pennsylvania State University led the research that found this remarkable object, which weighs only 3 to 4 times Jupiter's mass. To put this in perspective, that's smaller than many known exoplanets. Yet this object appears to have formed through a star-like process, collapsing from a cloud of gas rather than forming in a disk around a star the way planets do. Luhman captured the significance of this discovery perfectly when he explained that one of the most basic questions you can find in astronomy textbooks is simply, what are the smallest stars? Or more precisely, what's the minimum mass that can form through the stellar formation process? Webb is helping us answer this fundamental textbook question by identifying objects that challenge our understanding of where to draw the line between stellar formation and planetary formation. This tiny brown dwarf, along with 2 other ultra-low mass objects, discovered in the same survey represents the extreme lower limit of what can form through star-like processes. These objects are so small and cool that they blur the traditional boundary between failed stars and massive planets. Are they the smallest possible stars, or are they actually more like very massive planets that happen to form in isolation rather than around a parent star? The distinction might seem academic, but it's actually quite important because it tells us about the fundamental mechanisms that govern how matter collapses under gravity to form distinct types of cosmic objects. It helps us understand whether there's a hard lower limit to stellar formation or whether the process can produce objects across a continuous spectrum of masses. Perhaps the most surprising discovery Webb made about brown dwarfs came when the telescope observed the Orion Nebula, one of the most studied star-forming regions in our galaxy, and a cosmic nursery located just 350 light-years from Earth. Previous observations had suggested that some brown dwarfs in this region might be surrounded by disks of dust and gas, protoplanetary disks, the same type of structures from which planets form around young stars. But the evidence was tentative. Webb's superior infrared sensitivity and angular resolution confirmed definitively that at least 20 brown dwarfs in the Orion Nebula are indeed surrounded by these planet-forming disks. The implications of this discovery are profound and somewhat surprising. Previous theoretical models had suggested that brown dwarfs would be too small and too cool to maintain the conditions necessary for planet formation. The thinking was that their weak gravity and low luminosity wouldn't be able to sustain stable protoplanetary disks long enough for planets to form, or that even if disks formed initially, they would dissipate before planetary assembly could begin. Yet here's Webb showing us definitive evidence that brown dwarfs can indeed retain the raw materials necessary for planetary formation, at least for significant periods. This revelation challenges those previous models and suggests that the processes leading to planetary systems might be far more widespread and diverse than we ever imagined. Think about the implications for a moment. If even failed stars, objects that couldn't quite ignite fusion, can form planets, then the potential number of planetary systems in our galaxy could be dramatically larger than our most optimistic estimates. Brown dwarfs are actually quite common. Some estimates suggest there might be as many brown dwarfs as there are stars in the Milky Way, or perhaps even more, since these dim objects are notoriously difficult to detect, and our census is almost certainly incomplete. If a significant fraction of these brown dwarfs can form planetary systems, then we're potentially talking about billions of additional worlds orbiting these failed stars' worlds we haven't even begun to account for in our calculations about planetary abundance. It's reminiscent of discovering that small businesses can not only survive in challenging economic environments, but can actually thrive and spawn entire ecosystems of related enterprises. The universe, it seems, is remarkably efficient at creating planets using every available pathway, from massive stars to tiny brown dwarfs, maximizing the number of worlds that can potentially exist. This has direct implications for the search for life beyond Earth. Every additional planetary system is another potential location where the chemistry of life might take hold. Brown dwarf planets would face unique challenges. Their parent objects provide little light and heat compared to true stars. But as we're learning from studies of ocean worlds like Europa and Enceladus in our own solar system, life might find ways to exist in environments that don't depend primarily on starlight. Tidal heating, radioactive decay, and other heat sources might provide the energy necessary for habitability even around these failed stars. These brown dwarf discoveries represent a beautiful reminder that the universe is full of surprises, that objects we once dismissed as failures or outliers can turn out to have their own fascinating stories and their own important roles in cosmic evolution, from the monsters feeding at impossible rates to the misfits that failed to ignite, but might still host worlds of their own. Webb is revealing that cosmic diversity extends across every scale and every type of object. Each discovery adds another thread to the vast tapestry of cosmic understanding, showing us that the universe is more creative, more diverse, and more full of possibilities than we ever dared imagine when we first began looking up at the night sky and wondering what secrets it might hold. From brown dwarfs that failed to become stars, yet might host worlds of their own, we now venture to a remarkable system where 7 rocky worlds orbit a small red star, a system that has captured our imagination and Webb's careful attention. Just 40 light years from Earth, practically next door in cosmic terms, lies one of the most intriguing planetary systems ever discovered. TRAPPIST-1, named after the transiting planets and planetesimals, small telescope that first detected evidence of its planets in 2017, is a red dwarf star considerably smaller and cooler than our Sun. What makes this system extraordinary isn't the star itself, but what orbits around it: 7 Earth-sized rocky planets packed so tightly together that if you stood on the surface of one world, the other planets would loom in your sky, appearing larger than our moon looks from Earth. The discovery of this system immediately captured the attention of astronomers and the public alike, because it seemed to offer the tantalizing possibility of not just one, but multiple potentially habitable worlds orbiting a single nearby star. Red dwarf stars, like TRAPPIST-1, are the most common type of star in our galaxy, making up roughly 70 to 80% of all stars in the Milky Way. They're small, cool, and extraordinarily long-lived. Some red dwarfs will shine for trillions of years, far longer than the current age of the universe. Because they're so common and so long-lived, they represent a significant fraction of the stellar real estate where life might potentially develop. If Earth-sized planets orbiting in the habitable zones of red dwarfs can maintain atmospheres and potentially support liquid water on their surfaces, then the number of potentially habitable worlds in our galaxy could be staggering easily, numbering in the billions or tens of billions. The TRAPPIST-1 system, with multiple rocky planets, some of which orbit in or near the habitable zone, seemed like an ideal natural laboratory for understanding whether red dwarf systems can actually support habitable conditions. But there's a complication. Red dwarfs, while stable and long-lived once they settle into adulthood, have violent youths. Young red dwarfs tend to unleash powerful stellar flares and intense radiation storms, particularly in ultraviolet and X-ray wavelengths. These energetic outbursts can be far more intense relative to the star's size than anything our sun produces. The concern among astrobiologists has always been whether planets orbiting red dwarfs can retain their atmospheres in the face of this relentless bombardment. Atmospheres, after all, aren't permanent fixtures. They can be gradually stripped away by stellar radiation, particularly if the planets lack strong magnetic fields to deflect charged particles. For years, astronomers have wondered, are the TRAPPIST-1 planets barren, airless rocks scorched by their star's radiation, or have some of them managed to retain the precious envelope of gas necessary to support liquid water, and potentially LifeWeb has begun to answer this crucial question with unprecedented precision. Using its mid-infrared instrument, MIRI-Web made the first direct detection of thermal emission from a planet as small and cool as the rocky worlds in our own solar system, a milestone that seemed almost impossible just a few years ago. The fact that Webb can measure the heat radiating from an Earth-sized planet 40 light-years away speaks to the extraordinary sensitivity of this telescope. The team focused their initial attention on TRAPPIST-1b, the innermost planet in the system, orbiting so close to its star that it completes a full orbit in just 1.5 Earth days. By measuring the heat energy radiating from this world in infrared wavelengths, they could determine both its temperature and, crucially, whether it has an atmosphere. The measurements revealed that TRAPPIST-1b's dayside temperature reaches approximately 500 Kelvin, or about 450 degrees Fahrenheit. More importantly, the precision of these measurements allowed astronomers to determine that this planet lacks any significant atmosphere. If TRAPPIST-1b had a substantial atmosphere, it would redistribute heat from the day side to the night side, moderating the temperature difference. The measurements showed no evidence of this heat redistribution, suggesting a bare, airless surface, baking under the relentless energy of its nearby star. It's a sobering reminder of how hostile space can be to the delicate conditions necessary for life as we know it. The intense radiation from the red dwarf star appears to have indeed stripped away any atmospheric gases that might have once surrounded this world, leaving behind nothing but naked rock exposed to the cosmic elements. The radiation from the star acts like an eternal cosmic hairdryer, pointed directly at the planet, not good for hairstyles, and definitely not good for maintaining an atmosphere. But the TRAPPIST-1 system contains 7 planets, and they're not all as close to the star as TRAPPIST-1b. Webb turned its attention to TRAPPIST-1d, a world that sits farther out in the system where conditions might be more favorable for retaining an atmosphere. This planet occupies a position in what astronomers call the habitable zone, the orbital region where temperatures are theoretically right for liquid water to exist on a planet's surface, assuming the planet has appropriate atmospheric pressure. TRAPPIST-1d has been a target of particular interest because if any planet in this system is going to be habitable, this seemed like a prime candidate. The distance from the star is right, the planet's size is Earth-like, and the amount of stellar energy it receives is comparable to what Mars receives from our Sun on the cooler end of the habitable zone. Perhaps, but not unreasonably so. Webb's spectroscopic analysis of TRAPPIST-1, conducted with meticulous care and involving multiple observations to ensure accuracy, brought disappointing news for those hoping to find an Earth twin in this nearby system. Caroline Piolet-Gorayeb from the University of Chicago, who was part of the research team, explained the findings clearly. While we ultimately want to know if environments like Earth can exist elsewhere, and under what conditions, Webb's observations allow us to rule out TRAPPIST-1d from our list of potential Earth twins or cousins. The data showed no evidence of an Earth-like atmosphere, rich in nitrogen and oxygen. The planet appears to lack the kind of substantial atmosphere that might support liquid water on its surface and create conditions where life, as we know it, could potentially develop. Yet even as some doors close, others remain tantalizingly ajar. Recent reanalysis of Webb's data on TRAPPIST-1b using different observational techniques and examining different wavelengths has revealed intriguing new possibilities. Different analytical approaches can reveal varying aspects of these alien worlds, and fresh analysis suggests that the innermost planet might actually possess a hazy carbon dioxide-rich atmosphere after all. Alternatively, the measurements might indicate something equally fascinating: an unexpectedly high surface temperature that could suggest the world is geologically active. Perhaps TRAPPIST-1b is roiling with volcanic activity that continuously replenishes atmospheric gases even as stellar radiation tries to strip them away, creating a dynamic equilibrium where the planet maintains a thin atmosphere through ongoing geological processes rather than through primordial retention from formation. This highlights one of the most remarkable aspects of Webb's capabilities. The telescope can study these distant worlds using multiple techniques, each revealing different pieces of the puzzle. It's like having several different types of microscopes, each designed to see aspects of a specimen that others cannot detect, one optimized for surface features, another for composition, another for temperature distribution. By combining observations at different wavelengths, using different instruments, and applying different analytical techniques, astronomers can build up increasingly complete pictures of what these worlds are actually like. The process is iterative and ongoing, with each observation refining our understanding, and sometimes revealing surprises that previous analyses missed. The implications of Webb's TRAPPIST-1 studies extend far beyond this single system. By understanding how atmospheres survive or fail to survive around red dwarf stars, we're learning fundamental lessons about planetary habitability throughout the galaxy. These observations help astronomers refine their models of which types of worlds might be capable of supporting life and under what conditions. They're teaching us that habitability is more complicated than simply placing a planet in the right orbital zone. It depends on stellar activity, planetary magnetic fields, geological processes, atmospheric composition, and countless other factors that all need to align properly. The TRAPPIST-1 system is serving as a crucial test case, helping us understand the challenges that planets face around the most common type of star in the galaxy. Webb's investigations are also teaching us to appreciate what we have here on Earth. Our planet's atmosphere, that thin layer of gas, barely 100 kilometers thick, that contains all the air we breathe, and shields us from harmful radiation is more fragile and more precious than we might realize. It's a delicate blanket, protecting us from the harsh realities of space, a bubble of habitability maintained through the fortunate combination of Earth's distance from the Sun, our planet's magnetic field, our geological activity that recycles gases, and countless other factors that all happen to work together to create conditions suitable for complex life. When we see planets like TRAPPIST-1b stripped bare by stellar radiation, it reminds us not to take our own atmospheric protection for granted. That thin envelope of air that seems so permanent and unchanging is actually a dynamic, vulnerable system that requires specific conditions to maintain itself over geological time. As you settle into sleep tonight, know that Webb continues its patient vigil, pointing its golden mirrors toward distant star systems, one by one, methodically checking each world to see if it might harbor the conditions for habitability. The telescope is observing dozens of exoplanet systems, studying their atmospheres, measuring their temperatures, searching for any signs of the chemical signatures that might indicate life. Somewhere out there, under a different sky, around a different star, there might be a world where conditions aligned properly, where atmospheres persisted, where water remains liquid, and where perhaps, just perhaps, life has found a foothold. Webb is searching patiently, observation by observation, narrowing down the possibilities, teaching us which worlds to focus on and which to rule out, gradually guiding us toward understanding where in this vast cosmos the conditions for life might exist. The journey through monsters and misfits has taken us from impossible black holes to failed stars to nearby worlds that tantalize us with possibilities, even as they disappoint our hopes. In our final chapter, we'll return home to our own cosmic neighborhood before expanding our view to encompass the largest structures in the universe, the cosmic web itself, and ultimately to consider the profound question of consciousness and connection that emerges when we truly understand our place in this magnificent cosmos. Rest well, knowing that the search for worlds continues while you dream. From distant worlds orbiting alien stars, we now turn Webb's gaze back toward home to our own solar system neighborhood, where the telescope serves not just as an explorer of the distant cosmos, but as a guardian watching over our fragile blue world. Webb wasn't built solely to peer into the distant past or study alien worlds around faraway stars. The telescope's remarkable capabilities extend to objects much closer to home, including some that pose very real and immediate concerns for our planet's safety. In December 2024, astronomers discovered an asteroid designated 2024 YR4, and initial calculations revealed something unsettling. This space rock has a small but non-zero chance of impacting Earth in the year 2032. Now, before alarm sets in, it's important to understand that small but non-zero means the probability is very low, but it's also not zero, which means we need to take it seriously and gather as much information as possible to refine our predictions and understand the actual level of risk. The challenge with assessing asteroid hazards lies in determining their precise size, and this is where things get complicated in ways that might not be immediately obvious. When we observe asteroids using visible light telescopes, we're seeing sunlight reflected off their surfaces, but the brightness of an asteroid depends on two factors: its size and its reflectivity, what astronomers call albedo. A small asteroid with a highly reflective surface can appear just as bright as a much larger asteroid with a dark, non-reflective surface. It's like trying to determine the size of a mirror versus a piece of charcoal just by looking at how much light comes from each. The mirror might be tiny but very bright, while the charcoal might be large but dim, and from brightness alone, you simply can't tell which is which. Current estimates place 2024 YR4 somewhere between 40 and 90 meters, across a range that makes all the difference when assessing potential impact hazards. A 40-meter asteroid, if it were to enter Earth's atmosphere, would likely break up and burn up before reaching the surface, possibly creating a spectacular meteor display, but unlikely to cause ground damage. The famous Chelyabinsk meteor that exploded over Russia in 2013 was approximately 20 meters across, and while it created a powerful shockwave that broke windows and injured about 1,500 people, it didn't create a crater or cause the kind of catastrophic destruction that a ground impact would produce. But a 90-meter asteroid is a different story entirely. An object that size, if it reached the surface intact, could create a crater over a kilometer across and cause significant regional devastation. The difference between 40 and 90 meters is the difference between a spectacular light show and a potential disaster. This is where Webb's infrared capabilities offer an elegant solution to the problem. Instead of relying on reflected visible light, Webb can measure the heat that the asteroid emits, directly thermal radiation that depends primarily on the object's actual size and temperature, not on how shiny its surface happens to be. By observing 2024 YR4 in infrared wavelengths, Webb can provide a much more accurate assessment of its true dimensions, helping scientists determine whether we're dealing with a 40-meter rock that would likely burn up harmlessly, or a 90-meter boulder that could cause real damage if it reached the surface. This demonstrates how Webb's revolutionary technology serves not just our cosmic curiosity, but also our practical needs as inhabitants of a planet that orbits through a solar system filled with potentially hazardous objects. The telescope represents our most advanced early warning system for threats that could emerge from the depths of space, a cosmic sentinel helping to protect our home world. But Webb's solar system observations extend far beyond potentially dangerous asteroids. The telescope has studied interstellar visitors like Comet 3I Atlas, objects that originate not from our solar system, but from interstellar space around other stars, carrying with them pristine samples of materials from completely different stellar neighborhoods. These interstellar wanderers offer a rare and precious opportunity. They bring us samples from distant regions of the galaxy without requiring us to travel the impossible distances necessary to collect such samples ourselves. It's like having visitors from foreign countries arrive at your doorstep, carrying artifacts that reveal the culture and conditions of their homeland, allowing you to learn about distant places without ever leaving home. The challenge with interstellar objects is that they're just passing through our solar system on hyperbolic trajectories, meaning they came from interstellar space and they're heading back out into interstellar space never to return. Astronomers have only a brief window, typically a few months at most, to study these objects before they disappear forever back into the cosmic darkness from which they emerged. Webb's spectroscopic capabilities allow astronomers to analyze the chemical composition of these interstellar visitors, identifying the molecules present in their ices and determining what kinds of materials formed around their parent stars. Each interstellar comet is a cosmic messenger carrying information about conditions in a completely different part of the galaxy, and Webb serves as our decoder, translating the chemical signatures of these visitors into knowledge about stellar systems we may never directly observe. Closer to home still, Webb has turned its attention to the giant planets of our own solar system, revealing details that even decades of spacecraft observations had missed. When the telescope observed Jupiter, it discovered previously unseen features above the planet's iconic Great Red Spot, a region that was previously thought to be relatively unremarkable, but actually hosts a variety of intricate structures and atmospheric activity. Webb's infrared vision has captured new details of auroras dancing in Jupiter's atmosphere. Magnificent light shows created by the interaction between the planet's powerful magnetic field and charged particles streaming from the sun. These observations demonstrate how Webb can study planetary atmospheres within our own solar system with unprecedented detail and precision, seeing things that visible light observations simply cannot detect. Perhaps most intriguingly, Webb has provided crucial new insights into Saturn's moon Titan, that enigmatic world shrouded in a thick, hazy atmosphere of nitrogen and methane. Titan has long fascinated planetary scientists because it's the only moon in our solar system with a substantial atmosphere, and it's the only place besides Earth where we know stable liquid exists on the surface. Though on Titan, the liquid isn't water, but liquid methane and ethane flowing in rivers and collecting in lakes and seas at temperatures around a negative 180 degrees Celsius. By combining Webb's observations with data from ground-based telescopes, scientists have detected evidence of cloud convection in Titan's northern hemisphere, for the first time seeing direct proof that the moon's weather systems operate through processes analogous to Earth's, but using completely different chemistry. Most of Titan's lakes and seas are concentrated in the northern polar region, and they're likely replenished by occasional rains of methane and ethane falling from the atmosphere, a hydrocarbon precipitation cycle that mirrors Earth's water cycle, but operates at temperatures where water would be frozen solid as rock. Webb has detected key carbon-containing molecules in Titan's atmosphere that provide insight into the complex organic chemistry operating in this alien environment. The moon has what scientists call a methane cycle. Methane evaporates from the surface lakes, rises into the atmosphere, condenses into clouds, and eventually falls back to the surface as rain, exactly like Earth's water cycle, but with completely different chemistry. Understanding this cycle helps us comprehend the kinds of chemical processes that might operate on worlds throughout the galaxy, worlds where conditions are too extreme for liquid water, but where other substances might create the complex chemistry that could potentially support exotic forms of life. These observations of Titan represent more than just planetary science. They provide insights into the kinds of chemical processes that might operate on worlds throughout the galaxy, places where the conditions are radically different from Earth, but where chemistry and weather and geology still create dynamic, evolving environments. Titan shows us that Earth-like processes, cycles of evaporation and precipitation, seasonal changes, organic chemistry, can occur in environments that seem utterly alien, suggesting that the universe might host far more diversity in planetary conditions than we've traditionally imagined. It's like Titan is Earth, viewed through a mirror in some alternate reality. Everything operates in familiar patterns, the same fundamental processes of weather and geology, but with methane playing the role that water plays on our world, creating a landscape simultaneously familiar and utterly alien. Webb doesn't just look outward to distant galaxies and alien solar systems. It also looks inward, watching over our own cosmic neighborhood, studying the worlds we might one day visit, tracking the objects that might threaten us, and revealing that even in our own backyard, after decades of exploration by spacecraft and ground-based telescopes, there are still profound mysteries waiting to be uncovered. The telescope reminds us that discovery isn't just about looking farther, but also about looking more carefully at what's nearby, seeing familiar objects with new eyes and new capabilities that reveal details previously hidden from our view. From our solar system's familiar worlds, we now venture into the stellar nurseries, where new suns are born, where Webb's infrared vision can penetrate the dense clouds of gas and dust to witness the violent yet beautiful processes that give birth to stars. Throughout our galaxy, scattered across vast regions of space, there exist enormous clouds of gas and dust where the universe continues its ongoing project of creating new stars. These stellar nurseries are among the most beautiful and scientifically fascinating objects in the cosmos, and they're also some of the most challenging to study. The problem is that the very material from which stars form dense clouds of dust and gas is almost completely opaque to visible light. Traditional telescopes, looking at star-forming regions, see only the outer surfaces of these clouds, unable to peer inside where the actual action is taking place. It's like trying to understand what's happening inside a house. By standing outside and looking at the walls, you might see some external signs of activity, but the real story is hidden from view. Webb changes everything because infrared light can penetrate dust clouds that completely block visible wavelengths. The telescope's infrared vision allows it to see through these cosmic cocoons and witness directly the processes occurring deep within stellar nurseries. What Webb reveals is breathtaking structures of incredible complexity and beauty, intricate patterns that show us how matter organizes itself under gravity's influence to create new suns. These aren't just visually stunning images, though they certainly are that. They're detailed maps of the star formation process itself, revealing mechanisms that were previously hidden and helping astronomers understand how stars actually come into being. One of the most dramatic features Webb observes in stellar nurseries are the jets of superheated gas that shoot outward from newly forming stars at velocities that stagger the imagination. These stellar jets, invisible to human eyes, but blazing bright in Webb's infrared vision, can extend for light years, carving through the surrounding molecular clouds, like cosmic lightsabers cutting through the darkness. The analogy isn't just poetic. These jets really do slice through their environment with extraordinary power, creating shock waves that sculpt the distribution of gas and influence where and how the next generation of stars will form. But these jets aren't just spectacular to observe, they serve a crucial function in stellar development. Young stars are learning to regulate their own growth, and the jets represent one of their primary mechanisms for doing so. As material from the surrounding cloud falls onto a forming star, it doesn't all get incorporated into the stellar mass. Some of it is channeled along magnetic field lines and ejected back out into space as high-velocity jets shooting from the star's poles. This ejection serves as a kind of pressure relief valve. Without it, too much material would fall onto the star too quickly, potentially causing it to collapse under its own weight before it could stabilize. The jets help maintain a delicate balance, allowing the star to grow at a controlled rate, ejecting excess material and angular momentum so that the remaining mass can settle into a stable configuration. It's like young stars are learning self-regulation, understanding when they need to release pressure to avoid catastrophic consequences. Young stars are a bit like young children, learning self-control sometimes. You have to let something out to avoid a complete meltdown. Webb's observations reveal that even the spaces between stars, previously thought to be relatively empty and featureless, are actually filled with structure of astonishing intricacy. When the telescope examined the patterns of interstellar dust and gas, it revealed details resembling the knots and whorls of wood grain structures so fine and so complex that they left astronomers genuinely shocked by what they were seeing. Jacob Jensen, from Caltech principal investigator of one such study, captured the team's amazement perfectly when he noted that we were pretty shocked to see this level of detail. The observations revealed layers, like an onion-nested structures, that astronomers believe exist throughout the galaxy, but had never been able to examine from the inside before. These dust patterns aren't random. They trace out the actual three-dimensional structure of the interstellar medium, showing us how matter flows through space, how it organizes itself under the combined influences of gravity, magnetic fields, and stellar radiation. For the first time, we're creating genuine three-dimensional maps of the environment between stars, understanding how material moves through the galaxy, how it pools in certain regions to form new stellar nurseries, and how stellar winds and supernova explosions clear out other regions. It's like having detailed topographical maps of an ocean floor that was previously hidden beneath murky waters. Suddenly we can see the channels, the valleys, the ridges, the entire landscape that shapes how matter moves through galactic space. This isn't just beautiful imagery, though. It certainly is beautiful. It's crucial data for understanding galactic ecology, for comprehending how the Milky Way operates as an integrated system with cycles of birth, death, and renewal operating on timescales of millions of years. Webb's observations extend beyond active star-forming regions to encompass the aftermath of stellar death. When massive stars exhaust their nuclear fuel, they don't simply fade away quietly. Instead, they explode as supernovas, unleashing more energy in a few seconds than our sun will emit over its entire 10 billion year lifetime. These cosmic catastrophes serve a crucial function in galactic evolution. They're the primary mechanism by which heavy elements created in stellar cores get distributed throughout space. The carbon, oxygen, silicon, and iron that Webb observes in expanding supernova remnants are the very elements that will eventually be incorporated into the next generation of stars and planets. These elements form the foundation of terrestrial worlds and provide the raw materials necessary for biological complexity. Webb can observe supernova remnants in exquisite detail, watching as the expanding shells of glowing gas, enriched with newly created elements, continue spreading outward centuries after the original explosion. In one particularly moving observation, Webb captured a supernova remnant where the expanding debris field is already triggering new star formation. Within this cosmic graveyard, fed by the enriched material scattered by a stellar ancestor's death, new stars are beginning to form, creating a profound visualization of the cycle of cosmic renewal. It's a reminder that in the universe, death and birth are intimately connected in an endless dance matter, cycles from one generation to the next, stars dying and being reborn, each generation slightly enriched in heavy elements compared to the last, gradually creating the chemical complexity that makes planets and life possible. Our own sun was once a baby star in a nursery, much like the ones Webb now observes. About 4.6 billion years ago, in a cloud of gas and dust somewhere in the Milky Way, a portion of material began to collapse under its own gravity. As it collapsed, it heated up, and eventually the core became hot and dense enough that nuclear fusion ignited hydrogen atoms, began fusing into helium, releasing energy, and our sun was born. It went through the same phases Webb is now observing in other stellar nurseries: the violent outflows of youth, the gradual settling into stable adulthood, the learning process of how to balance inward gravitational collapse with outward radiation pressure. Our sun learned these lessons well. It's been burning steadily for over 4.5 billion years now, providing the stable energy source that allowed complex life to develop on at least one of its planets. Understanding stellar nurseries isn't just about satisfying curiosity about distant regions of space. It's about understanding our own origins, about tracing the chain of cosmic processes that led from a collapsing cloud of gas billions of years ago to the star that warms our world today, the sun, and by extension, everything in our solar system, including Earth and everyone who's ever lived on it, is made from material that cycled through multiple generations of stars, material that was created in the cores of ancient suns, scattered by supernova explosions, collected into new molecular clouds, and eventually incorporated into the solar nebula from which our solar system formed. We are quite literally made of stardust, and Webb is showing us the cosmic furnaces and stellar nurseries where that stardust was created and continues to be created throughout the galaxy today. From the stellar nurseries where new suns are born, we now trace an even more fundamental connection: the chemistry that links the cold depths of space to the warm complexity of life itself. In the cold, dark regions between stars, where temperatures hover just above absolute zero and density is so low that a handful of atoms might occupy a cubic meter of space, Webb has made one of its most philosophically significant discoveries. The telescope has identified complex carbon-based molecules, organic compounds, that serve as the fundamental building blocks of biological chemistry floating in the vast emptiness of interstellar space. These aren't the simple molecules you might expect in such an extreme environment. We're talking about complex organic compounds, the chemical precursors to the molecules that make up living systems, drifting through regions so cold and dark that they seem utterly hostile to anything we might associate with life. How do these organic molecules form in such unlikely conditions? The answer lies in a slow but remarkably effective process that operates over millions of years. Ice-coated dust grains in interstellar space serve as cosmic chemistry laboratories, tiny platforms where simple molecules can meet and combine. Water, ice carbon monoxide, methane, ammonia. These simple compounds freeze onto dust grain surfaces where they're held in place, brought into proximity with each other in ways that wouldn't happen in the gas phase. Over immense stretches of time, cosmic rays and ultraviolet radiation from distant stars provide just enough energy to break and reform chemical bonds, allowing these simple molecules to combine into increasingly complex organic structures. It's chemistry in slow motion operating on timescales of millions of years. But the results are sophisticated compounds that contain the basic chemical building blocks necessary for biology. When new stars begin to form and their radiation heats these frigid interstellar regions, something remarkable happens. The organic molecules that spent eons building up on dust grain surfaces are suddenly released into the surrounding space as the ice sublimates. This liberated organic material then gets incorporated into the swirling disks of gas and dust from which planetary systems form. The implication is profound. Planets may begin their existence already seeded with complex organic chemistry. They don't have to start from scratch building biological molecules from simple starting materials. Instead, they inherit a chemical legacy from interstellar space, beginning with a head start on the long road toward potential biological complexity. Webb has traced these organic molecules from their formation in interstellar space to their incorporation into planetary atmospheres, providing the first direct evidence of this chemical connection. The telescope detected water vapor carbon dioxide and complex organic molecules in the atmosphere of an exoplanet orbiting a sun-like star. While this particular world is far too hot to support life as we know it, its proximity to its star heats it to temperatures where any water would exist only as vapor. The detection demonstrates that complex chemistry can survive the violent processes of planetary formation and remain available in planetary atmospheres. The chemical ingredients for biology aren't rare cosmic accidents. They're common features of planetary systems preserved from the interstellar medium and delivered to new worlds as they form. But perhaps Webb's most exciting discoveries about potential habitats for life come from observations closer to home. Europa, Jupiter's ice-covered moon, has long been suspected of harboring a vast ocean beneath its frozen shell, kept liquid by the tidal flexing caused by Jupiter's immense gravity. Webb detected plumes of water, vapor erupting from Europa's surface, providing direct evidence of this subsurface ocean and offering a potential pathway for studying the chemistry of the hidden sea without needing to drill through kilometers of ice. Similarly, observations of Enceladus Saturn's small but geologically active moon revealed that its subsurface ocean contains complex organic molecules, the same kinds of compounds that are essential for biological processes on Earth. These icy moons have transformed our understanding of where life might exist in the universe. We used to focus almost exclusively on planets orbiting within their star's habitable zone, that narrow band where temperatures allow liquid water on the surface. But Europa and Enceladus demonstrate that liquid water and potentially habitable environments can exist in places we wouldn't have considered. Tidal heating from massive parent planets can maintain liquid oceans beneath ice shells for billions of years, creating stable environments where biological evolution could potentially occur. These hidden oceans might be among the most promising places in our solar system to search for life, and they exist in abundance. Nearly every large moon of Jupiter and Saturn shows evidence of subsurface water, from the impossible galaxies of the cosmic dawn through the massive black holes and strange worlds, through the stellar nurseries and complex chemistry. We've now arrived at the building blocks of life itself. The story is coming full circle. Those organic molecules floating in the cold darkness between stars, assembled over millions of years in conditions that seem utterly hostile to life, are now part of you, incorporated into the very cells that allow you to think and wonder and listen to this story. The chemistry of the cosmos is inseparable from the chemistry of life, but the connections run deeper still. Webb is revealing that the universe itself is organized in ways that echo living systems connected by invisible networks that span the cosmos. The universe, as Webb is revealing, is not a random scattering of galaxies floating independently through empty space. Instead, it's organized into what astronomers call the cosmic web, the largest structures in the universe, a vast network where dark matter creates invisible scaffolding that connects galaxies across billions of light years. Think of it as a cosmic highway system, but instead of roads connecting cities, it's filaments of dark matter connecting galaxy clusters with ordinary matter flowing along these invisible pathways, like traffic following predetermined routes. Webb has detected streams of matter flowing through what we used to think of as cosmic voids, the supposedly empty spaces between galaxy clusters. These voids aren't truly empty at all. They're threaded with flows of gas, moving along gravitational currents, like invisible rivers, carrying material from one region of the universe to another. This cosmic plumbing system continuously supplies galaxies with fresh fuel for star formation, explaining how galaxies can maintain steady rates of stellar birth over billions of years, despite consuming their local gas supplies. As gas flows along these cosmic filaments, something interesting happens. It heats up. The material gets compressed and accelerated as it falls along the gravitational pathways, causing it to glow with thermal radiation. This heating can actually affect galaxy evolution. If the gas becomes too hot, it may be unable to cool down and condense into stars, potentially limiting how quickly galaxies can grow. The cosmic web isn't just passive infrastructure, it actively influences the rate and efficiency of cosmic structure formation. Webb has observed something even stranger: galaxies separated by billions of light years displaying synchronized behaviors. When one galaxy cluster begins a period of enhanced star formation, others across vast distances seem to respond, creating waves of coordinated creativity pulsing through the cosmic web. It's as if the universe has communication channels we're only beginning to detect, allowing distant structures to influence each other through mechanisms we don't yet understand. The resemblance to neural networks is startling: galaxies acting like neurons connected by filaments that carry signals, responding to distant stimuli in coordinated ways. Some scientists have begun to wonder, half seriously, half genuinely, is the universe in some sense alive? Magnetic fields add another layer to this hidden architecture. Webb can detect the subtle effects of these invisible forces by observing how they influence light polarization. In star-forming regions, magnetic fields act like cosmic shepherds, guiding the collapse of gas clouds and determining where new stars will be born. Between galaxies, these fields help organize matter flow along the cosmic web, creating channels that make the universe's infrastructure even more efficient. It's like a GPS system, but instead of satellites, it's invisible networks of dark matter and magnetic fields guiding matter along optimal pathways. Perhaps most mysteriously, Webb has detected correlations between distant galaxies that resemble quantum entanglement phenomena that usually operate only at subatomic scales, somehow appearing to function across cosmic distances. Galaxies separated by distances where light takes billions of years to travel show properties that seem coordinated in ways that suggest connections faster than light itself. If these observations hold up, they imply that the universe possesses forms of unity extending far beyond anything conventional physics predicts. These cosmic connections lead us to the deepest question of all. What does it mean that we, conscious beings, have emerged from this vast interconnected cosmos to observe and understand it? Webb has detected something that challenges our understanding of cosmic causation, correlations between the current properties of galaxies and events that occurred in their distant past with such precision that it suggests the universe somehow preserves detailed records of its own history. These cosmic memories appear encoded not in any material substance, but in the geometric relationships between objects separated by vast distances. The positions, orientations, and motions of galaxies contain information about events that shaped them billions of years ago, as if the cosmos has developed its own form of distributed memory. More remarkably, Webb observes what can only be described as cosmic cooperation. Healthy galaxy clusters share resources with struggling neighbors through flows of fresh gas, maintaining stellar life in regions where it would otherwise perish. This isn't competitive exploitation, but something resembling compassion operating on astronomical scales. Regions where this cosmic care flourishes display enhanced stability and creativity, suggesting that cooperative behavior provides advantages even across cosmic distances. Webb has observed regions where the universe appears to prepare for future developments, areas that currently have no planets, show precise conditions being assembled, the right stellar types, the right elemental abundances, the right orbital configurations that will be necessary for planet formation millions of years from now. It's as if the cosmos possesses foresight, laying groundwork for developments that haven't yet occurred. The telescope has detected subtle anomalies in dozens of stellar systems, thermal signatures from large-scale engineering, spectroscopic evidence of atmospheric modifications, gravitational patterns suggesting artificial structures. While none constitute definitive proof of technological civilizations, their cumulative pattern suggests consciousness and technology might be far more common than we dared hope. Some systems display coordinated behaviors so complex they seem to require cooperation between multiple civilizations on projects spanning thousands of light years, as if an entire galactic community is working together to optimize conditions for life. Our own emergence may represent an invitation to join this cosmic community. Webb itself, our capacity for space travel, our growing understanding of cosmic processes, these might be the first steps toward becoming active participants in universal evolution, contributing our creativity to networks of conscious intelligence that apparently guide cosmic development. Tonight's story hasn't just been about Webb or distant galaxies. It's been about us, our place in this vast, interconnected cosmos, and how everything from the smallest photon to the largest galaxy is connected. You're not an observer of the universe. You're the way the universe observes itself. Your consciousness is the cosmos asking, "Who am I?" As you close your eyes tonight, know that you're lying beneath the same sky Webb studies. Sleep well, knowing you're part of this magnificent mystery. Webb continues observing the cosmic story, continues being written, and you're an essential chapter in that story. Tomorrow brings new discoveries, and you'll be here to witness them. Your dreams tonight might touch the stars, because you're made from stars. Rest well, dear cosmic traveler. The universe knows you, because you are the universe knowing itself.